import of the mechanism of the Poynting vector to describe the propagation of a plane electromagnetic wave, or any wave really, but particularly a plane, and that the direction of propagation is consistent, means, as I said before we got started, we can sort of reduce the propagation in a particular medium to that direction of propagation. We can draw the whole scenario with just a ray, just a directed line segment. In this chapter, we start that. What are we talking about in this batch of slides? Oh, which reminds me, I also need to get a prop. What are the colors about? What does it have to do with the speed of propagation? And how can we make that all useful for us? In the discussion of a mechanical wave on a string, we talked about wavelength. We talked about the distance in space between corresponding points on a wave, whether that's crest to crest or trough to trough. We talked about the wavelength. Not all the points that have the same phase are crests. Not all of them are troughs. In other words, not all of them are maxima of the oscillating field. Not all of them are minima. But if we collect all the points of a spherically propagating electromagnetic wave that are in phase with each other, those phase loci, I suppose, are in the shape of spherical shells. And we can talk about the successive sort of shell instances as wave fronts. Spherical wave fronts spread out uniformly in all directions from a point source. Electromagnetic waves do that also. We were talking about plane waves. The Poynting vector associated with this propagation is radial. It's spherically radial, and it best described using spherical coordinates. It is in the radius direction. Just like we talked about a radially symmetric distribution of charge on an insulating sphere, for example, we might be interested in using spherical coordinates to talk about the Poynting vector and the direction of propagation being not along the x-axis, but along the radial direction. Drawing wave fronts is difficult. They are 3 or 2-dimensional, and as we saw in the previous batch of diagrams, they were rectangular planes that were stacked. It's hard to draw, but the x-axis, that particular direction of propagation, that's not so bad. And even for spherical wavefronts, we could sort of representationally decide to represent them not as spheres, but as projections of spheres onto the XY plane, for example, such that they would be circles. All right. And if they're circles, then we could represent the circles again with radii, always perpendicular to the wave front. That's key. The wave fronts in their representation are perpendicular to the direction of propagation, just like they were in the previous batch of drawings, just like they are here, just like they are in this picture as well. If we are very, 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 very far away from a point source of spherical radiation, just as the surface of the Earth appears to be flat as we look at it because we are very, very, very far away from the center of a spherically shaped object, the wave fronts appear parallel and sort of rectilinear, and the rays that represent the propagation are parallel to each other. We call this a plane wave. A plane wave happily traveling along in one medium might encounter an interface, a boundary between that medium and another medium. It may reflect off that boundary. It may propagate through. It may do both. If it propagates through, it might propagate in an altered way, having to do with the fact that it has moved from a medium of one, what did we call it? Index of relative speed. That it is moving from one medium into another where the relative speed of the propagation might be different. How does that change things? In general, there is non-zero reflection and transmission. We could talk about the reflection and transmission coefficients if we wanted to, and consider ideal cases, I suppose, perfectly reflecting, perfectly transmissive boundaries between substances, but generally there is some transmission and some reflection. Generally. It's often the case that the transmitted wave is altered by the differences between the media, and we could call it refraction, but it is just transmission according to the laws of electromagnetism. That's all it is. It's transmission. We might be familiar with this already, calling it refraction. Reflection does not only occur from a smooth surface. It's easiest to spot if it occurs from a smooth surface. We can see it upon inspection, and we call it specular reflection. It allows a certain fidelity of image that diffuse reflection does not. The walls of this room, for example, do not function like mirrors. I cannot see if I look at this mirror, or there is no mirror there. But if I look at this wall, I don't see a reflected image of the stuff behind me, because this is a diffuse surface and is subject only to diffuse reflection. Almost everything is visible at all because of diffuse reflection. Only certain things are visible participant in specular reflection. And it's almost like those specular those surfaces that obey specular reflection are less visible in and of themselves than the reflections that they permit. If I regard my face in the mirror, I don't really see the mirror itself. I have to sort of focus on the surface of the glass, and so I almost have to touch it to verify that it's there. What I see is not the mirror itself, really. What I see is the reflected image, the reflected light. So an object visible to me in and of itself is probably the result of diffuse reflection. Having said that, even though that's the thing where we kind of rely on to see shit, mathematically, it's hard to describe because it's not regular. It's specular reflection that we're particularly interested in here because it obeys a regular law that describes its behavior. And that law is simply that the angle of incidence and the angle of reflection have to be equal. And you can think about this roughly in terms of, well, Newton's second law. Think about a ball thrown at a wall. The wall is able to apply a force perpendicular to itself only. It is able to exert impulse in the perpendicular direction, not in the parallel direction. The vertical component of the velocity of the pointing has to be preserved because there's no way for the surface to have interacted with it. We can change the direction along the axis perpendicular to the wall, but we cannot change the direction along the axis parallel to the surface of the wall. That means that these angles need to be the same. Now, if there is a transmitted ray, if some of this wave also moves into medium B, then we might be able to talk about the relative amplitudes of these various waves. You could think of it like a junction rule in a circuit, for example. We have some amount of energy coming in, and we're going to bifurcate, send some energy back and some energy through the other medium. So we can change the amplitudes of these waves. We can change their intensities, their brightness as we perceive them, but we cannot change the relative angles because we have no mechanism by which to do so, at least as far as specular reflection is concerned. So the law of reflection is just a statement of a thing hitting a wall, basically. We have defined already the index of refraction, which we know is the index of relative speed. For the case shown here, material B has a larger index of refraction and the angle theta B is smaller. Okay. Why? Okay. Apparently, it is because of a law. Apparently, Willebrord Snell wrote down this thing in the, late 16th century, and it's a law. Turns out the law was actually first discovered in the 10th century by a Persian scientist, Ibn Sahl. But I guess we don't call it Sahl's law. Um, and I'm not entirely sure why. Now, this is one of those things that I'm really surprised the Young and Friedman textbook doesn't just prove this. It's not hard. It takes a few minutes. So let's do that. Maybe if I can hold on to the pen. Suppose we have a ray of light propagating in this direction towards a boundary, an interface between two media. Suppose it is the case that the index of refraction is larger in the second medium. Now, n sub b is the speed of light in a vacuum divided by the speed of light in medium B. Which I think means, if we can cross multiply, that the speed is actually greater in medium A. We also know, for any given wave, that when we talk about the propagation speed, we could also talk about the frequency and wavelength. I'll give the frequency individual subscripts, one for each medium. However, the red ray is in fact the, I guess you could call it the Poynting vector, but it's the direction of propagation. These blue lines are the wave fronts. So we've got a plane wave here. We could label the wavelength. It's the distance between successive wave fronts. And the thing is that this is a wave. And if we consider, let's say, this point at the boundary, in medium A, our wave is propagating with some frequency, which means that in some amount of time from right now, when let's say that the wavefronts are maximum values of the electric field, at time zero, the electric field is maximum. And then as time goes on, these wavefronts advance. And the electric field oscillates at this point, this purple point here, from its maximum value through 0 to its minimum value through 0, and then back to its maximum value right as this next that next wave front gets there. So we are giving this point on the boundary of the media explicit instructions. What is the magnitude of the electric field at U? And we know that it varies in an amount of time from maximum to maximum, according to the period, according to the frequency of the wave as it's propagating in medium A. But this point at the boundary is also in medium B, and it would be really difficult to imagine the electric field, which really ought to be single valued since it's a function. We took a derivative of it. In order for it to have a different rate at which it oscillates at this point at the medium boundary. If the point on the boundary is in fact to not have split personality disorder, the time between successive maxima of the electric field has to be constant. Like whether we're on one side or the other side of the boundary, there has to be, otherwise we've got like a particle here at the boundary that's trying to do two things simultaneously at different rates. And I don't know if you have ever tried imagine holding the hands of people next to you, and one person is jumping at a particular rate and the person on the other side is jumping at a different rate. How are you supposed to jump to make that work? Should you jump at this rate or this rate? It's not, you're like stepping your feet at different times. It's the whole thing. Like it requires tearing your brain in half. I don't know, it wouldn't work. This thing that I'm talking around is the requirement of continuity at the boundary. What that means is that the frequencies have to be the same. So I don't need those subscripts. Now, that means that these points along the boundary still need to be a wavefront apart. They need to be a wavefront apart and also closer together somehow. Because the wavelength in medium B has to be smaller. There's only one way for that to happen. They have to bend. So that this new wavelength is smaller. It's the only way for that to happen. It's the only way to preserve continuity and have the wavelength be smaller. One more line I gotta draw with the ruler here. And that is the perpendicular to the boundary. Three is enough. All right. I'd like to consider some angles. I'd like to consider the angle oh wait, there is one more thing I should draw. The ray that represents the propagation perpendicular to these wave fronts. I'm going to draw it here. For simplicity, we usually draw only one ray, but there are actually a whole collection of parallel rays that are all perpendicular to all these wave fronts. And one of them hits this spot and propagates away in this direction. Ah. Perpendicular to those wave fronts. Now, we know some things. We know that this distance, I'm talking about triangles now. I'd like to talk about that triangle. And that one. This leg of the top triangle is lambda A. This leg, the orange leg here, is lambda B. I'd like to talk about this angle. I'm going to call it theta B. And I'd like to call this angle theta A. These are both right triangles because the ray is perpendicular to the wavefront. And this bit along the boundary of the medium is common to both. It's the hypotenuse of both triangles. You know what? I think I'm making things complicated for myself. Can I consider the other acute angle in these triangles? Is that all right? Can I consider this one theta A and this one theta B? Such that if we follow along, with the geometry of things, this angle is theta A, the angle between the perpendicular to the surface, to the boundary between the media, the angle between that and the ray coming in. And then this angle is theta B. Is that real? That doesn't look real. Well, if that's the theta B that I want, this, I had it right. Oh, but only on this side. This angle here is 90 minus theta B. But this angle here is 90 minus that, which gets us back to theta B. So what do we know? We know that the sine of theta B is the opposite side, lambda B, over the hypotenuse. I'm just going to call it x for now. We also know that the sine of theta A is the opposite side, which is lambda A, over the hypotenuse, x. So that's the same x, that green highlighted side, and that means we can solve the system, or I guess eliminate it from the system, I suppose. Well, that's a little bit backwards. I didn't expect cross-pollination of A and B. At least that wasn't how Sal's law was presented to us. But that's okay because lambda and n have an inverse relationship to each other. If we multiply both sides of this equation by f, we can replace that with the speed in medium B and the speed in medium A. And if we look back to n equals c over v, the speed v is c over n. So this is c over nb sine theta a, c over na sine theta b. If we cancel c and cross multiply one more time, we end up with Snell's law. It's actually not that, I don't know. I mean, it's just geometry, isn't it? Geometry and the fact that we are requiring our electric fields to be continuous at the boundary. They need to have a definable derivative, such as, and remember back, like the fundamental definition of derivative. If the derivative exists, that means the left-handed and the right-handed limit have to be the same. So that means we've got to have the same story on one side and the other, in time, right? Okay. There we are. Snell's law. Like I said, it doesn't take long. But the Young and Friedman text that I'm looking at, I can't find the derivation here. I'm sort of surprised. A ray entering a material of larger index of refraction bends toward the normal. Bending toward the normal means that the angle between the ray and the normal decreases. Normal, again, is an old word that just means perpendicular, like normal force, right? That's what we saw in the derivation just now. It's a little bit confusing to go from the one to the other. In this case, the boundary between the media is a vertical line, not a horizontal one. That's why it appears to be kind of backwards, what we just did. But if we orient ourselves, we do in fact bend in order to decrease the angle between the ray and the perpendicular to the boundary between media. If we go the other way, it bends away from the normal. Sine of 0 is 0. And the only way to satisfy the version of Snell's law so that 0 equals something is sine of the other angle also has to be 0. In the case of normal incidence, there is no refraction. There is no bend. Why does a body of water appear shallower than it is? Why does a ruler appear bent? Because our eye only knows where it looks like the light came from. The end of the ruler appears to us to be at a shallower depth than it actually is, which means the angular orientation of the ruler has changed and it looks like it's bent. Indices of refraction are a little bit dependent on the frequency in question. If we use yellow light, then these are the indices. Water is very nearly 4/3, 1.333. Air is just about 1. Air is very similar to vacuum in that respect. We said that for any given material, for any given medium, lambda and n are inversely related. what is going on here? If we are traveling from one region to another region of lesser index of refraction, we take a look at Snell's law. We are interested in the angle of the refracted ray in medium B, so we isolate that variable and we ask for the inverse sine of the result. NA over NB sine theta A, inverse sine of that equals theta B. No, not a problem. Suppose we're going from water to air such that NA is 1.333 and NB is basically 1. Suppose also that the angle of incidence is 85 degrees. Make it 80 even. Suppose that the angle here, theta is theta A, suppose it's 80 degrees. What is theta B? And A is 1.333 divided by 1 times the sine of 80 degrees. Make sure I'm in degrees. Take the inverse sine of that. And my calculator says error. Because there's a domain problem. This turns out greater than 1. There is an angle, theta critical, when it is exactly equal to 1, and the answer is 90 degrees. And the transmission occurs along the interface between the two media. That's what's happening here. If the angle of incidence in medium A is greater than the critical angle, no transmission is possible. So I said almost all the time. In this case, transmission is mathematically prohibited, and we have to reflect all of the incident energy back into medium A. It never reaches medium B. Only if we're going from high to low index. This is the principle behind fiber optics. As long as the curvature is not too great, we never encounter a spot along the wall where the angle of incidence isn't greater than the critical angle, and none of the energy we are transmitting leaves the cable. We said that the speed the index of refraction in a particular medium depends a little bit on the wavelength of light in question. We can see that the wavelength for silicate crown glass, for example, varies over the range of visible light from about 1.525 to about 1.5. The dependence of wave speed and therefore index of refraction on the wavelength in question is called dispersion. Now, let's think about this together with Snell's law. If the angle of, okay, wait a minute. If the index of refraction for a given wavelength is different than that for another one, that means that the refracted angle for one wavelength might be different than the refracted angle for another one, which means that even if we have a whole bunch of different wavelengths incident all in one wavefront, I suppose, all in one ray, we could theoretically separate them angularly by the differences between the indices of refraction at the different wavelengths. We could quite literally disperse, spread out the constituent components of the incoming light. Which is exactly what happens whenever we see a rainbow. This picture helps explain why it is most common to see a rainbow when the sun is behind you and the rain is in front of you. We need to be standing here so that we can see these dispersed wavelengths. But that means the water droplets need to be ahead of us and the light needs to be behind us. At slightly different incidence angles, slightly different colors are internally reflected, and those different internal reflections disperse the colors for us. Two reflections from the back surface of the droplet. So we enter the drop, bang, bang. Those two reflections end up with a mirroring effect. And if you see a double rainbow, look closely. The order of the colors is reversed. Anybody who skis a lot or fishes a lot or engages in water sports or other winter sports, or maybe drives a whole lot for work will tell you that a pair of polarized sunglasses makes so much difference. In a prior life, I used to work at Sunglass Hut. And that was fun because I could tell everyone why polarized lenses were the better thing to do. If the electric field has only one vector component, we can say that it is linearly polarized. Light from most sources is a whole superposition of waves with components in all kinds of different directions. Unpolarized or natural light, there is no preferential direction. A polarizing filter restricts the transmission to only the component that aligns with the polarizing axis of the filter. I have a pair of sunglasses here. It's I had this, okay, I said it was in a prior life, right? I got this pair of sunglasses in 2006, maybe 2007, like the winter of 06, 07. And I had them for 12 years, give or take. Until finally the one temple broke. But I can't quite get rid of them. The other thing they're good for is physics demonstrations. If I hold the lens up to the camera, you can see me through it. That's because the light that is hitting my face is subject to diffuse reflection and is completely unpolarized. The light from my tablet, on the other hand, is not natural light. If I put the lens between the tablet and you and the camera, again, you can see through it, unless we change the angle of orientation. And that blackness there is the result of crossed polarization. The light from the tablet is already polarized in large part. And the polarizing filter of the sunglass lenses, if we put them at cross purposes, the sunglass lenses allow very little transmission. And you can see that here, Malice's law. Hold on, let me go back and find out how many slides I skipped. Oh, just one. Okay, cool. Polarized light of initial intensity I is incident on a polarizing filter. The intensity depends on the angle between the polarization and the polarizing filter. In this case, the polarized light of intensity I max, that's in this region. I max passing through the analyzer is reduced in intensity according to Malice's law. The first polarizer to achieve the polarization actually functions to decrease the intensity by a factor of 2, according to the way averages work around the incident unpolarization. Essentially, on average, we reduce the intensity by a factor of 2. That's not what is described here in Malice's law. That's just a intensity reduction according to the fact that there's stuff in the way, and that we only permit certain allowances to go through. Once we have polarized the light linearly such that it has, at this point, some maximum intensity I max. If it goes through the analyzer, the angle between the analyzer's filter and our new linear polarization, that's angle phi, and the new intensity is by cosine squared of that angle. Why are polarized sunglasses a good idea? Reflection, a lot of the time, especially when it is specular, off of or very well, yeah, or approximately specular, like off the surface of water, or off the surface of snow, or off a wet road surface. There is a polarization, a linear polarization that results from the reflection. The light for which the electric field lies in the plane of incidence is not reflected at all, but is completely refracted. When that angle happens, the reflected ray is polarized linearly without any other components, polarized linearly. Which means we can block it with polarized filters. Why is it better to winter sport, fish, drive, especially at night? There have been multiple times when driving at night in the rain, I have put on my sunglasses because the headlight and streetlight glare off the wet road is worse than it being slightly darker. If I can get rid of that glare off the road, oh, it's so much more comfortable. When the vector E has a constant magnitude but rotates around the direction of propagation, we can call it circularly polarized. Think phasors here. The old school 3D glasses were different colors, red and blue. That's maybe not the best because you don't achieve color fidelity that way. You're filtering everything through red and blue. So if we use circular polarizers, we can differentiate one lens from the other lens, and now your brain is actually seeing two images and is overlaying them, and it looks three-dimensional. That's because what's coming at you is circularly polarized two different ways. And then if we use polarizers, the other, like in that particular way, we can restrict one set of incoming waves for one eye and one set for the other eye. Absorbed and then re-radiated, let's call that scattering. Clouds contain a high concentration of suspended water droplets or ice crystals, meaning that all the wavelengths are scattered pretty much equally. But air molecules scatter blue light preferentially. So the sky looks blue. This last slide is about Huygens principle. I'm actually going to save I suppose. I'm going to save Huygens principle. We're going to use it more in the next chapter. I mean, I guess we're just going to move to the next chapter right now, so I guess it's fine. We can model a wave front as a collection of many, many, many little point sources. Each of those point sources emits circular waves, circular wavefronts. So this source here has a propagation wavefront associated with it. This source here has a propagation wavefront. This one has a propagation wavefront. And if we collect the sort of the loci of all of those different second like propagation wavefronts, we end up with the overall second wavefront of the larger source. So we're treating the propagation of the waves from a single source back here somewhere as sort of stepwise propagation from individual sources collected on a wavefront. Each of those sources makes a new thing, and then we have a new wavefront, and then each of those sources makes a new thing, and we have a new wavefront. We could use Huygens principle to derive the law of reflection geometrically. We could use it also to derive the law of refraction, although I think the argument from continuity is more persuasive because Huygens principle feels a little bit squishy. It's only a model. The other one was pretty true. But it does, like, we can't get away from the fact that Huygens principle is useful in certain circumstances. Like describing a mirage. The hot air very near the ground has a smaller index of refraction than the cooler air above it. So light travels fastest near the ground, which means that the light along the way continues to bend away from the normal. And it might, in fact, bend all the way away so that it never actually hits the ground. And we could interpret that reflection that we sort of see like it is off a surface of water, for example. This also happens on asphalt on warm days. It looks like there's a whole puddle of water across the road. And then when you get closer to it, there isn't. This is when it's happening. Questions, comments, concerns?